There are various ways to do it. You could do it by trying to find a peak. So going along that line of thought, we could set y final to 0. That's when it's going to hit the ground. If there was no wall there, we could solve for how long it takes to hit the ground again. And then we can look, half of that time is when it hits its peak. And we can see if that is more than, let's see, if that's less than 20 or more than 20 meters. Or, sorry, we have found a time, right? We can look to see if it's more than our 1.31 seconds or less than our 1.31 seconds, right? Did it hit its peak before it got to the wall or after it got to the wall? But I think the easiest way is, you have a suggestion?
For the Y final, I got a different answer.
Oh, what'd you get?
8.49.
Anybody else?
I got
8.14. Is that better? So it clears the wall. Is that the verdict? Clears the wall, okay. And so it clears it by 3.14. Right? Okay, we have agreement. Now, is it going up or coming down? I think the easiest thing is right here. Solve for V final and look to see if it's positive or negative. If V final in the y direction is positive, it's going to be going up. If it's negative, it's going to be coming down. Is V initial plus AT, right? Initial was positive 12 point something, 9. What do we get? Close. It's right around the peak, right? Positive, is that what you said? 1.6? 0.16, yeah. It's very close to. So it's still going up. Okay. Okay, let's do this. We'll take a 10-minute break, and then we'll do a little demonstration, two-dimensional kinematics, and then we'll move on to forces. Let's move on. I didn't check this number. 8.14, I'll take your word for it, but I went back and double checked this number. It was not what I got. I got 0.062 meters per second, but I did get positive, so those answers are the same. Okay? All right, two-dimensional kinematics. Tell me this. We've got two projectiles being launched simultaneously. A and B. And B travels a path, let's see, going to run out of room here. A travels a path that looks something like that. And B travels a path that looks something like this. Which one hits the ground first? Launch them simultaneously. Even, let's see, talk it over. What was your logic on the first one? What determines the time? You know what I like to do? Picture it from the top here. We did this demo the other day, right? We have, let's pretend we have that little gizmo I had here the other day. It dropped one marble straight down. It shot the other one out to the side, right? Let's pretend that's right here. There's one. There's the other one. So this object, 1 and 2, huh? 1 drops straight down, hits the ground, and 2 is given a horizontal velocity and follows the blue path, hits the ground right there. Which one hits the ground first? Same time. Why is that? They both have the same y velocity to start with. They both have the same y acceleration. So they both take the same amount of time to cover that same distance in the y direction, right? How about if we did the same thing over here, 3 and 4? How about 1 and 3? Which one takes longer? Okay. So which one hits the ground first? A or B? Can we do the same thing here? One and 2. Three and 4. Oops. 4 is given a big horizontal velocity. How about 3 and 4? They hit at the same time, right? How about 1 and 3? So, B hits first. We good with that? You want to see it? I've got a low projectile that's going to hit about the middle of the desk here. You ready? Did you catch that? Came up right about here, right? Landed somewhere in the middle of the desk. Okay, it goes very high, lands about the middle of the desk. Okay, we ready? We'll launch them simultaneously. Okay, 3, 2, 1. Was that obvious? Yeah. Which one hit the ground first? The lower trajectory, right? Thank you, appreciate it. Okay. Steve, you need that one more time, or you got it? Okay. All right, so higher trajectory. And it doesn't matter where they hit. Now you can aim them such, like I did here, such that they hit in roughly the same spot. You could get them to hit in exactly the same spot. Okay? The one that goes higher takes more time, or you can have a situation like this. I just couldn't, in the confines of the room and the springs and those launchers, I couldn't quite get this situation to set up. But you could get it to set up like this, and the one that takes the higher trajectory takes longer because the time is determined by the y direction. Okay. No, not necessarily. Not necessarily. It definitely not in this case. No, sorry. You could have it in this case. You could, when the angles add up to 90 degrees, they land in the same place. And I'm told, I grew up in Los Angeles, so I'm not an expert on snowball fights, but I'm told that there's a technique when you're in a snowball fight, you get 2 snowballs. You get 2 snowballs, and you throw the first one like this, and you throw the second one with a low trajectory. And while your opponent is doing this, at the first one, the second one nails them. And I can tell you that I took my kids up to the snow when they were a little younger, and it works really well on 10-year-olds. It works really well. But past that age, I think they catch on pretty quickly. But up till then, they don't have to be, actually in either of these situations, they don't have to be the same initial velocity. If these angles add up to 90 degrees, the angle that A makes and the angle that B makes, then, and they're the velocities are the same, then they'll land in the same place. But they don't have to be the same initial velocity.